I'll mute everybody.
Alright, it's fine now.
Right.
Okay, it's fine now.
Okay, that was some teething problems. So we're going to start from the beginning. And we're starting a quarter of an hour late, and we're going to have half an hour less for lunchtime. So it'll be about an hour and a quarter for lunchtime instead of 2 hours. Okay. We restart at 2:30 after the lunch break. And our first speaker today is Mike McCulloch from the University of Plymouth, who's going to talk about Pull of the Distant Horizon. Okay, start from there.
Well, thank you, thanks for inviting me. Okay, so I'm going to talk about what inertia is, theory of quantized inertia, astronomical evidence for it, and then lab experimental evidence, and then I'll talk about applications as well. Okay. So the problem I started from many years ago was that galaxies spin faster than physics expects. So here's a representation of a galaxy spinning around. This is one star within it, and they can tell how fast the stars are moving from the Doppler shift, and they can work out the centrifugal force that's being exerted on them. And it seems that the matter within the galaxy is not enough to pull the star back in. So the gravitational force is much less than the inertial force outwards. So galaxies should fly apart, but they don't. So the popular solution, of course, is to add dark matter to the galaxy, make it more massive, say there's hidden invisible matter, which boosts the gravitational force to balance the centrifugal one. But I don't like this solution because dark matter is very arbitrary. It's just added at the edge of the galaxy and in places to make general relativity work, and I don't think this is good scientific practice. So I've been thinking about the old mystery of inertia. So inertia it's always been assumed, never really understood why things keep moving in the same direction. And inertial mass is not due to the Higgs field, which only explains the mass of the quarks. It's about 0.1% of the total mass. So I proposed a new model for inertia, which combines relativity and quantum mechanics. So this is a... Okay, so this is the model. This is an object, this black circle, and if you imagine it's accelerating to the right, then according to quantum mechanics and relativity, according to Bill Unruh in Canada, this object will see what's called Unruh radiation, which is a kind of heat bath, thermal random radiation, which I've tried to represent here with the red colour, and so some of this radiation will impact on the object. The object, according to relativity, will also see a horizon here. So this black area represents a part of the universe that is not observable by the object because light cannot catch up with it because it's accelerating away. So this is a bit like a black hole event horizon, and it will split virtual particles and it will produce this Unruh radiation. So this is all linked. But the new assumption I'm making is that this horizon damps the radiation. So I've tried to represent that with this blue colour. So close to the horizon we have a cold blue space, and on this side of the object we have a warm space with lots of radiation, lots of Unruh radiation. This means that the radiation will hit the object from this direction, but not so much from this direction. So it will see a thermal flux of radiation pushing it backwards against whatever acceleration it has. And I've managed to show in this paper here that this looks just like inertial mass. So it predicts inertial mass. Okay. So, because I'm using Unruh radiation, I guess I need to justify this, and very luckily for me, in a brilliant experiment, Unruh radiation was actually seen last year by Lynch et al. So what they did was they fired high energy positrons into a silicon crystal, so like this. The crystal decelerated the positrons extremely fast, and they saw radiation emitted. I've shown here by the red. And looking at the spectrum of the radiation, Lynch et al. Were able to show that the data, the observed spectrum, so the dots here, looked exactly like Unruh radiation, what was expected for Unruh radiation. So this is the first observation of Unruh radiation. So it is a real thing. Okay, so there is a slight amendment at very low acceleration to quantized inertia. So if you have an object with a very low acceleration, then the Rindle horizon will move away. So the lower the acceleration, the further the Rindle horizon is away. And if it moves behind the cosmic horizon, so this is the horizon which is very far away that we see at the edge of the universe, about 10 to the 26 meters away, then the Rindle horizon no longer matters. And what happens now is this cosmic horizon now damps Unruh radiation all the way around equally, and so the phenomenon we know as inertial mass should disappear for very extremely low accelerations. So what should happen is that the inertial mass you see should be the original one times a factor which depends on the acceleration of the object. So when A becomes very small, this term blows up and the inertial mass reduces. So I showed that in a paper back in 2007. And it turns out that this exactly compensates for this galaxy rotation problem, because the stars at the edge of the galaxy are accelerating very slowly. So according to quantized inertia, their inertial mass is reduced and their centrifugal force is reduced by exactly the amount needed to balance gravity. So it works perfectly. So I published a paper in 2012 on that. And then this is another paper from 2017 that I published showing that if you look at the expected acceleration of stars and galaxies and the observed acceleration, for low accelerations the observed acceleration is much higher than expected. So these grey squares, the data rise above the line of equality there, and the theory predicts it exactly, predicts the data exactly. Theory predicts that the edge velocity of stars should be given by this formula here, and everything in this formula is known. So obviously gravitational constant, this is the baryonic mass of the galaxy, speed of light, the Hubble scale, which is known to within 5% or so. So the theory has only one chance to be right, and it's perfectly right. It predicts galaxies exactly. So that was this paper from 2017. So just a more direct piece of evidence, smoking gun if you like. So this is a galaxy, and in the centre the stars are accelerating very rapidly because the circle is tight. So the Unruh waves they see are quite short, so I've shown that here. As you go further out into the galaxy they lengthen, and at exactly the radius in the galaxy where these waves become the size of the cosmic horizon, that's exactly the point at which galaxies start to deviate from standard physics, which is a prediction of quantized inertia, and it's in every single galaxy. So it's a very direct piece of evidence for it. Okay. So recent work I've done, I've managed to derive quantized inertia from information theory. So I'll just show you how I've done that. So the energy you get from deleting one bit of information is kT log 2. So this is Landauer's principle, by the way, which has been verified by looking at the deletion of information in computer memory. It releases heat. So now, if you imagine that we have an object, so I've shown this object as a line, actually, but you'll see why in a minute, with Planck length bits along it, and then imagine it's not accelerating at all, so it sees all the way out to the cosmic horizon, so 10 to the 26 meters out, and I've assumed that information is stored in spaces the size of a Planck length, because this is the smallest length of space that you can store information in, you can't see, you can't observe anything smaller than that. So if you count up the number of bits you can see, these green dots, then if you imagine it accelerates to the left, and a Rindler horizon forms here, this blue line, so now it can see fewer bits, the purple dots. So it's lost a certain number of bits. And we can calculate how many bits it's lost. So if you like, the change of energy, the number of bits it's lost, is kT times n1, so this has come from this formula here. If we delete n bits, it's kT log 2 to the power n, which is ktn. So the change of energy, because of the change in the number of bits you can see, is given by ktn1 minus ktn2. ktn1 is the number of bits to the cosmic horizon, so that's the cosmic horizon divided by 2, because it's the radius divided by the Planck length, number of Planck lengths. And n2 is the distance to the Rindler horizon, which is c squared over a divided by the Planck length. So if you stick all this in and do some algebra, you get this. And then if you divide this line by, if you work out the number of bits in this line and divide by that, then you get this formula, which is the quantized inertia formula. It's exactly the same. So it seems that when you accelerate, the horizon comes closer, chops off some of the bits that you now can't see, and the amount of information that Landauer says you get from that is exactly equal to the mass or mass energy that quantized inertia needs. So I published that in 2020. So quantized inertia also predicts cosmic acceleration, because if you take this formula and you use maybe secular gravity laws, you get something like this. So the acceleration is the normal gravitational acceleration, or whatever acceleration you want, plus a constant term, 2c squared over theta. And this turns out to be the size of the cosmic acceleration that they see at the edge, at the cosmic edge. And also, it's an additional acceleration that is independent of mass. So we're not strictly breaking the equivalence principle here. So if Galileo dropped two balls of different mass from Tower Pisa, they would still fall together. It's just they would fall slightly faster. Okay, so this is the great thing about this, apart from the deeper understanding of inertia, is that if we understand inertia, we can perhaps control it. So we can produce a new kind of thrust. So I've proposed that in a couple of papers. And the basic idea is this. So if you have some kind of cavity and you put something in there which is highly accelerated, then it will see a lot of UNRU radiation. The more the better. So we have a red background here. And then if we put a damper in, which could be something as simple as a metal plate, then it will damp the radiation and we'll have a gradient. The radiation will push on the object. It will tend to move down the gradient. So this would be a propellantless alternative to rocket launchers. So there are several ways you might try to do this. So I'm sure you've all heard of the Casimir effect. Well, maybe you could put two plates very close together and have a current passing across. Then the UNRU radiation will be damped in the centre of the two, between the two plates, and that should affect the dynamics of the electrons, and I'll get back to that in a minute. Or, for example, you could have a crystal which has very fine crystal structure above and a very coarse crystal structure below, and then you would expect a gradient in the damping of the UNRU radiation, which will push it up. Or you could have a cavity with microwaves resonating within it, which is asymmetric, so that the narrow end will damp UNRU waves more than the wide end, and then you would get a thrust towards the narrow end. Or perhaps you could have a couple of plates, one of them thick, one thin, and you make a piezoelectric vibrate. UNRU radiation is formed, but it's damped more by the thick plate than the thin, so it should move towards the thick plate. So there are possibly several ways to do this. So when I started talking about this, DARPA got in touch and I applied for funding, and I got 1.3 million to try and prove this in the lab. So that's what I've been trying to do for the past 4 years or so. And we've learned, in this project, we've learned from experience. So we tried putting laser light into cavities, but the thrust we got from this was extremely small, or zero. But several groups have also tried using capacitors, and I'll talk about that in more detail, but this has been more successful. And I think I now understand why. So if this is a couple of plates and this is under radiation, you imagine there's some acceleration here, they're damping it between them, you can work out the force that you're going to get. So this is the Casimir force equation, but you need to make a change in the case of under radiation. Normally we have this action of the quantum field, h bar, but now we don't just have the background quantum field, we have a high acceleration and we have a lot of under radiation. So what I've done is I've put that into this formula by changing h bar, taking account of the acceleration we've got. So this is the energy you're putting into the system, this is the time it stays in there, and you can work it out, and h bar becomes the power you put in times the quality factor of the cavity, which is how many times the accelerator bounces around inside. D is the separation, or the distance between the two plates, and V is the speed of the accelerant, the accelerated object. And if you put this into the Casimir formula, you get something like this. And what's interesting here is this term, which I'd neglected before. I just assumed that everything was moving at the speed of light, but actually this V here is the speed of the object. And if you have something like a photon, then obviously it's the speed of light, so this becomes 1. But if you have an electron, then V is small, so this term becomes large, and so you get far more force. So for example, when we were firing, when a lab in Germany that was working for me under timer fired lasers into cavities, then the theory predicts about 0.4 nanonewtons, and that's about the same size as what they were seeing. You can see that in the paper here. So this is extremely small, but if you look at an experiment by Takaki Musha from 2008, he had 2 plates and he was accelerating electrons across between the plates. Then, according to the formula, you should see 14 millinewtons, and that's about what he saw. I think it was 10 millinewtons that he saw. So that's obviously a lot bigger in force. So Frank Becker and Anke Batt, they contacted me and read my papers, and they tried a capacitor setup in their lab. So they had a capacitor here on a digital scale, and they were applying about 5 kilovolts, 10 microamps, and they were accelerating electrons across a dielectric. So the idea here is to get the electrons to jump across very fast, so it's a huge acceleration, so only waves are seen. And the prediction is for about 5.6 millinewtons, and as you'll see, they saw about 6 millinewtons. So this is a plot of their results from their paper in 2018, and so this shows the confinement distance here, and this shows the normalized force. So when the plate separation was about that's about 100 micron, they saw a very small force. And as they decreased the separation to about 10 micron, they saw a much larger force, about 6 millinewtons as predicted. And this is also 100 newtons per kilowatt, which is a very large force per watt. Ion drives, the dominant in the satellite industry, the dominant thruster in the satellite industry gives about 0.02 newtons per kilowatt, so this is much better than an ion drive. So what I think is happening in this case is that normally if an electron accelerates, then it sees UNU radiation and a horizon behind it, and the UNU radiation is damped behind it by the horizon, so there's a pushback, and that's inertial mass. But in the case of the capacitor plates create an area where there's very little UNU radiation because the waves just can't fit in that gap. So now there's a blue area here and a black area here, so the electrons get an extra push forwards. And then when they hit the anode, they push the whole system. So I published that on ResearchGate here last year. So a very good test was done by Becker and Batt. What they tried was, as they're accelerating these electrons between the plates, and the Windler horizon is here, they put a baffle behind, between the horizon and the plates, and they found that it pulled the electrons back a little bit. It changed the thrust. But as soon as they moved the plate behind the horizon, which you can think of as an intellectual thing, a horizon is not a solid object, it's a calculated position. But as soon as they moved the baffle behind the horizon, its effect on the electrons disappeared. So I think this is the first observation of a horizon. So you can work out what force you're going to get from these capacitor thrusters. From quantized inertia, starting from the Casimir effect, you change h bar in a similar way, and you get a formula that looks like that. And I should say this is not empirical, this number, it's just a concatenation of the electron mass, the electron charge, and other things in this part of the formula. But this is the prediction, so we can now test this. And this is what it shows. So this is the separation of the capacitor plates. This is the force, and the black diamonds show the observed data. So you can see it's an exponential increase of thrust as you bring the plates closer together. And the theory, or this formula, predicts the squares. So it works pretty well. So the error bars I've shown with the shown on there. So I've published this on ResearchGate there. So it works very well, and it seems that the closer you move the plates, the more force you get. So Becker and Batt's initial experiment was confirmed and enhanced by Richard Mansell of a company in the US, a capacitor manufacturing company called IDO Limited. So to get rid of digital artifacts and the digital scale, they used a pendulum instead. So they had the capacitor on a pendulum, and they looked at slight movements of the capacitor from side to side. And they tested in a vacuum at Fredericksburg, Virginia. They talked to myself and Becker and Batt as they were doing it. They confirmed the results, so it's the second lab result. And I can't tell you what it is, but they used a new dielectric. One of the problems with the capacitor with a plastic dielectric is the plastic burns out very quickly, so they used a much better dielectric. And what they saw agrees with quantized inertia very well. So this is the increase of voltage that they applied. This is the thrust they saw, and the observed is a black line and predicted is a blue line, so it works very well. Okay, so now in Plymouth we're also testing this. So we have a system like this. We have the capacitor inside a shield, and the objective is to have it completely remotely operated so there are no wires going in or out. And we haven't quite achieved that yet, but we're fairly close. We have a digital balance, a USB, obviously a PC for analysis. So the capacitor is made from aluminium foil, and the dielectric here is usually either polyethylene or Kapton, so it's two kinds of plastic, and the separation is typically about 10 micron, but actually we're using 7 and 30 micron, but with the 7 it's probably about 10 in reality. Okay. So I had a postdoc, Dmitry Makhanovsky, produce a circuit which is shown here. QI sail is shown here, and it's powered by a 12-volt battery and DC to DC converter, which increases the voltage. So he's used a Raspberry Pi and ADC, and it can all be remotely controlled from a PC by a Python program with a VNC server. But at the moment this is not working, but it was for some of the earlier experiments. So what we do is we charge the capacitor up to a maximum of 3.5 kilovolts, and this is done in tiny increments because that avoids burnout. It's a very high voltage, and we can measure the leakage current as well. So this is an example of the leakage current. That's the voltage there to about 2 kilovolts, and this is the load current we see, less than a microamp typically. Okay. And this is what the setup looks like at the moment. So I have a new research assistant or research engineer, Richard Arundel, who's done an awful lot over the past 6 weeks. He's built new physical testing systems, improved the shielding, so this is the new shield box, if you like, transparent box. We've eliminated electrostatic effects as much as we can, improved capacitor manufacture, and he systematized the data recording. And if you want to see some of his YouTube videos, they're all on his channel. And we've completed 50 tests in six weeks, so he's worked very well. So that's his YouTube, some of his YouTube videos that you can look at. And this is how he manufactures the capacitors. So this is the dielectric, which is 10 micron thick plastic. Then we have the foil to put on it. We have felt, and then we have 2 perspex pressure plates to keep them pressed together, compacted. And then we use vacuum bags to produce a vacuum around the capacitor to get rid of any air pockets that might explode or cause artifacts. Okay, so the shield, as I said, is there, and this is the circuit. So some of the early experiments showed interesting effects. We had little explosions. You can see the foil was punctured here by something exploding out of the plastic. But we've managed to get rid of those sort of effects. And this is a summary of the 50 tests that we've made so far. So this is the applied voltage up to 2.5 kilovolts. And this is the thrust towards the anode. So we tried the capacitors in various orientations, both anode up and anode down, but to try and make sure that the thrust was following the anode, I've corrected all the data so it's all thrust towards the anode. This is about 8 milligrams of weight change. So the theory predicts that as soon as we get towards the breakdown voltage of the dielectric, then the effect should appear, because then the electrons start to rush across the gap en masse. So for 2 of these early experiments, 27 and 28 for example, you can see that it takes quite a high voltage to get a positive thrust. This is because we're using a 30 micron dielectric, so you need to get voltage up much higher. For the later ones, you can see that the positive thrust started to appear half to 2/3 of the voltage needed for the thicker dielectric. But the interesting thing is that we are actually getting a generally positive thrust. But I should say that this, I've used the later results because the earlier ones were full of artifacts. So from test 27 onwards we were doing far better. We had a better shield and we moved the electronics away, things like that. And a lot of maybe half the tests show no effect at all as we're going through. So here I've shown a test that showed a a positive result, not just 0. So I have selected for that, but all these tests that showed a result showed a positive thrust at about the right place and of about the right size. The theory predicts that for the thicker dielectric we should see a thrust in this blue box here, and for the thinner dielectric somewhere in the red box. So it's not too bad.
But there seems to be one negative.
Yes, that's right. So we need far more data to make this significant. Yeah, occasionally we do get negative thrust. But if you do take the average of these, and I've done that here, so this is the average of all the plots that I've shown you, which is probably a bit naughty because I've selected for the ones that show a signal, and I should include the ones that showed 0, which would reduce the peak, maybe about half, because half of them show no effect. But anyway, if you do look at them in this average form, you can see that when you get up to about 1 kilovolt, which is where the capacitors start to break down, you get a positive thrust. And this shows up the thinner dielectric. And then as you're higher, you see a second peak, which is for the thicker dielectric. So on average, it is positive. And you can see what this looks like. This is a result we got from the lab yesterday. I'm not sure how well you can see it, but this shows time on this axis, and then this is milligrams. You can see there's a sudden shift to a positive thrust there, and then a decline, and then a little negative peak, and 0 again. Okay, so just a word about possible applications. So this is the Dawn Spacecraft, which was famous because it used an ion engine, which produced about 90 millinewtons of force, but it was pretty heavy. It was half a ton and needed about 2 kilowatts of power to drive it. 0 to 60 in about 1 to 2 days, so it was quite a slow engine, but it's all they needed to get to zero. So we've seen about 0.1 millinewtons in our lab so far, but if you put this drive on for example, a CubeSat, you wouldn't need any propellant. All you need is electricity. You don't need to carry fuel. So it can be much lighter, and also it needs less than a watt to drive it. So you get to 0 to 60 miles per hour in about 9 days. So it's not too bad. It's not quite 1 to 2 days, but it's not that bad. Okay, so applications, fairly obvious, I guess. Satellite station keeping, CubeSat thrust, lighter satellites, flying cars. Easier, cheaper and safer silent launch if we can get the thrust large enough to actually launch something. Also, it's an interesting sort of thrust because in a normal rocket you fire your engines and you get pushed towards the back. But with a horizon drive, everything in the ship gets pulled forward at the same acceleration, so there will be no whiplash. Obviously this is a kind of energy from the vacuum. So for here I'm using it to produce thrust, but you can easily imagine that if you put it in a rotary system, you could generate electricity from it. But you need to put some in. And also, for the first time, it would make interstellar trips possible in about 10 years. That's because you don't need to carry fuel. So, okay, so to summarise, so quantized inertia explains inertial mass for the first time. It brings information into physics. So I showed you the derivation using information. It gets rid of dark matter and dark energy, which I didn't like very much anyway. It has excellent astronomical evidence, so galaxies, also wide binaries, globular clusters, they all agree with it. It predicts a horizon drive, and we've found that the capacitor thruster is the best approach, and we're seeing about 35 newtons per kilowatt in our lab and 0.1 millinewtons of thrust. Okay, so thanks for inviting me, and any questions?
The Zoom bit, so in case there was, let me see the Zoom. Thanks so much for that, Mike. I want to ask something. What's the significance of what you said about the proton mass or the baryon mass not coming from the quarks, and what's the significance of that in this? Does that matter?
Is that a comment where I said that inertial mass is not due to the Higgs field? Because
You said that about mostly about the main chunk of matter, protons and neutrons, presumably. Because
yes.
I don't agree with that personally, and I just wondered what the
Okay.
significance of that is.
Well, I suppose the significance for me is that standard physics claims that inertial mass is produced by the Higgs field,
Yeah.
and as far as I'm aware at the moment, it's only a very small component. If you disagree, that
I disagree with that. No, and the reason why I disagree is that if you write down a quantum mechanical model, not model, but expression for the baryon, you have three terms with plus or minus p in. P, X, P, Y, P, Z. And each of those can be either positive or negative equally, symmetrically. Now if you've got positive spin, as it were, positive angular momentum, and negative angular momentum at the same time, then you've got mass, because that's what the Higgs mechanism is all about. Now I think this rotation of the quarks inside the proton is done by that mechanism. And so it's not obvious that it's a Higgs field, but I think it still is.
okay. So you think Higgs field does account for inertial mass?
Indeed, yeah, of most of bulk matter. Yeah. Though I don't believe in
Okay,
dark. I'm interested in explanations of dark energy and dark matter, and not dark energy and dark matter. But I didn't think it mattered for your explanation.
Well, I suppose it matters because I came to explain inertial mass using horizons and under radiation. So if there's an alternative explanation on the Higgs, then obviously that's of interest to me.
I don't think alternative explanation rule out explanations. That's what I'm saying.
Yeah, sure. Yeah.
Yeah. People think that. They think, oh, we've got rotation of the quarks or something. That rules out anything else. It doesn't. It depends what is behind that. Do we have any questions from the Zoom participants? Okay. Go on at you, Lord.
Well, yes, I mean, I would say it's extremely exciting stuff. Great talk. One little thing that may be of interest is the aspect of saying, forget about quantum mechanics for a minute. Just look at the idea of space-time and how the Lorentz transformation treats periodic processes. If you do that, you come up with this funny thing that looks like a wave function, but in a sense isn't. It's straight out of classical physics. And it forces you to ask the question, well, is this really what wave functions in quantum mechanics are doing? And you can sort of answer that question by saying, well, okay, what would happen if you looked at the system through a double slit? And if you do that, you then have to say, well, what about the equivalence of inertial frames? You have to modify them and effectively say that okay, the equivalent of inertial frames has to be modified a little bit to account for the periodicity. So that if you look at paths between 2 points in space, then you can't think strictly in a sense of continuous paths because there's a period. So what that does is it says, in a sense, the vacuum can distinguish between even and odd. And so, in a sense, 2 paths, as long as they have the same parity, are okay in the scheme of things from the Lorentz transformation and transition from just a space-time to quantum. And that, to me, looks a little bit like your information processing and subtracting bits. It's not a matter of subtracting arbitrary lengths in a sense. It's about subtracting specific units of information. And when you do that, you get this equivalence, which in a sense allows from the transition from space-time to a quantum mechanical approach. And to me, that in a sense, that opens up quite a bit more of a vista of how not just very tiny things work, but large things as well. You know, not just at the subatomic scale, but you know, the sort of stuff that you're looking at, which is, you know, huge scales in a sense. So just a comment.
Yeah, thanks. That's interesting. My use of the Planck lengths was the sort of simplest way I could do it. But you're right. There's probably a lot more information out there that we could look at.
Chris?
I was just propel this propulsion, but you need to accelerate the electron propulsion gap. Are you harvesting photons, or what are you doing?
So harvesting UNU radiation,
Yeah.
which includes photons.
Oh, okay. So you're using that. Okay.
And then just making it inhomogeneous in space.
Okay. Okay, so my other question was, you were talking about the lunar horizon, about that's where the light before that can't catch up. So you're assuming it accelerates indefinitely, is that?
I don't need to do that anymore. There was a paper published recently, I can't remember the author, but they proved that you don't have to assume infinite time. These Windler horizons have an effect almost instantaneously on dynamics. So I could send you that paper.
Well, that's interesting because the horizon depends on what happens in the eventual future. That is that what you're saying?
The horizon only strictly, technically exists in the future of the object.
Yeah.
As you were saying, because
Yeah.
it takes some time for the photons to work out whether or not we can catch up.
That's right.
But actually, it's been shown that that's not the case. These horizons can have an instantaneous effect.
Okay.
Well, I can send you the paper
Okay.
if you're mind.
Okay.
Any further comments or questions from the floor or from Zoom? Okay, well, thanks very much for a very interesting presentation. We've got a few minutes before the next one due at 11. Do you want to start?